Welcome to another great O'Reilly webcast. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. Today, folks, we have Dr. Yves Hilpisch with us, and he is going to talk to you about derivatives analytics with Python. Yves has 10 years of experience with Python, particularly in the finance space. He founded the Python Quants GmbH, an independent, privately held analytics software provider and financial engineering boutique. He lectures on mathematical finance at Saarland University in Germany and is a regular speaker at Python and finance conferences. Folks, Yves is also the author of the brand new O'Reilly Media book, Python for Finance. We're very excited to have him with us today to present this webcast for you all. As we get the webcast started, I'd like to go over a little housekeeping to help you get the most out of today's webcast. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Yves. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Yves, please preface them with a capital letter Q so we know that it's for him and we can make sure we see it for Q&A. Also, folks, if you have any trouble with the webcast, please take a look at your help widget. If you continue to have trouble, just post it in the group chat and one of our staff will help you right away. If you would like to use the Twitter widget today, you might need to give it permission to access your account. The Twitter widget will automatically append the event's hashtag to your tweet so you don't have to. And today, folks, our hashtag is Python, all one word. If you have any trouble with the webcast, please take a look at the help widget. If you continue to have trouble, just post it in the group chat and one of our staff will help you right away. Folks, I'd like to let you know we are recording the webcast today, and we will have the recording ready usually within 48 hours. And at this time, it is my pleasure to turn the program over to Yves for his presentation. Hello, Yves.
Thank you, Yasmina, for the very kind introduction. My name is Yves Hilpisch. I'm very proud to be part of today's webcast with O'Reilly. It's been a long way for me personally and also for our company. Our company this year has a 10th anniversary when we started out with Python in the quant sphere at a time when almost nobody else was considering Python as a real contender programming language or ecosystem even in the derivatives analytics space. And now we have this webcast, we have the book out, we have so many things that are happening around the world with the use of Python that I'm pretty happy to present today the topic derivatives analytics with Python to you. I think Yasmina already shared the link to the presentation. I posted it on my private website, hilpisch.com. And there you find the HTML5 version, the web-hosted version of the slides as well. So if you later want to come back to the presentation, everything is there. Every single slide that I will present, you can find on my personal website. First, maybe a couple of words about myself. There was already the kind introduction. Maybe a brief overview again. I'm founder and MD of the Python Quants. We just recently renamed the company the Python Quants. It was called Physician beforehand, so you might find a couple of material on the web, which is with the former company name. But nevertheless, we're doing the same thing since a couple of years, and actually this around the world. You see, we even had recently in New York a For Python Quants conference, which was attended by more than 225 people, and which was a real success and will be maybe repeated at the end of the year or maybe autumn this year. Here you see also the link to my private website where you find lots of information about myself. Here the cover, so that you can remember it, of the new book with O'Reilly. I think you have already seen it on the webcast screen, so nothing new about that. But maybe also the cover of my other book, Derivatives Analytics with Python. There is a book page where we sell it in electronic as well as in printed form. This is more or less about advanced derivatives pricing models and the implementation of these models for the sake of simulation, calibration, and hedging of even complex options with American exercise, for example. So you find lots of material, also 5,500 lines of code within this book, which you all also get electronically if you're interested in that. But let us come to our topic of today, Python for derivatives analytics. My talk today focuses on Python for derivatives analytics, of course, but it's more like a prototyping-like algorithm implementation approach that I present. I will not go into details about like architectural issues or development processes or how to model different trades. I will focus really on the analytics side, being aware that there's so many issues surrounding that, trade execution, risk management, reporting, and others. But we will focus today here on Python and more or less on a rather interactive approach to derivatives analytics in that case. The agenda is as follows. We start with financial algorithm implementation, the two, let's say, canonical numerical methods, Monte Carlo valuation and binomial option pricing. We will then go on and show a couple of performance libraries that can be beneficially used in these application areas. I will then present, let's say, a couple of percent only of our new DX Analytics Suite, which is the first analytics suite of its kind, completely implemented in Python and targets the derivatives analytics space. It's completely Pythonic, but we will have a look at this rather closely in the third part. The fourth part is about web technologies, which are really beneficial when it comes to deployment of the analytics approaches that we present. And last but not least, I will have a couple of words about our new product, the Python Quant platform. Here again, the link, if you haven't found it yet, at silbisch.com, and there you find the full URL to the slides, but you should see it also on the webcast website and platform displayed. Financial algorithm implementation. The majority of financial algorithms, for example, in option pricing, can be formulated in array or, let's say, matrix setting, if we speak mathematically. And it's therefore paramount to have available flexible and fast array manipulation capabilities. I mean, one of the major prejudices when it comes to Python for analytics tasks is that Python is an interpreted language, which usually is not that fast when it comes to complex, like loop-heavy algorithm implementations. But NumPy is a wonderful tool which provides the basic infrastructure to implement these compute-intensive array manipulation capabilities. It provides actually the basic building blocks on which to build the financial algorithms, and almost any other library in the scientific stack or ecosystem builds on top of the NumPy and the array object. There are two major advantages of using NumPy in this context. The first is syntax. When you are able to vectorize your code, then typically you end up with much more compact, easier to write and also read and to maintain code, which in itself is an advantage. But on the other hand, you also get huge performance improvements typically, because the majority of the parts of NumPy is implemented in C and or Fortran, such that operations on the NumPy level are generally much faster than pure Python, which indeed is interpreted and can be pretty slow if you don't take care and do it in the, let's say, the wrong way or the not optimal way in a sense. But let us come to the first numerical method, which is really compute intensive, Monte Carlo valuation, used for tasks such as pricing, risk management, and so forth. Let's start with the, so to say, hello world example of the financial engineering space, which is the Black-Scholes model with the geometric Brownian motion as presented in the first equation here. We see an Euler discretization, which is exact in this case for the stochastic differential equation. We don't need to go into details. The implementation side is more important in the sense that when we want to simulate with pure Python, we first have a look at this and consider speed and also the code and how it looks like and what it means to have the simulation implemented in pure Python. We have to start with a couple of parameters. These are rather arbitrary. There's nothing about that. They're just like example numerical parameters. But we only use here in this case standard functions from the Python basic library actually. When we now implement the simulation procedure for, let's say, capital I different paths that we want to simulate, a simulation function might look at displayed on the screen. There are a couple of ways to implement it, but this is one of these. So what we're doing here is we have an outer loop, and this outer loop is over the single paths from 0 up until capital I minus 1. So we have capital I paths in the end, and in the inner loop we generate a path step by step over time. So nothing special about that. We collect all the paths that we simulate, and in the end end up with kind of a matrix with capital I simulated paths. So for example, if we simulate now 100,000 paths, this takes, with the pure Python approach, where we make only use of the standard Python library, where we use lists and lists of lists to store the data, this takes quite a while. This takes 20 seconds, a little bit more, almost 27 seconds to simulate it, and this is what you should remember as the benchmark. Of course, Python, and especially working with IPython Notebook, actually my whole presentation was done and generated with IPython Notebook. It's pretty simple to illustrate graphically a couple or a small selection of the simulated paths. Of course, usually you don't want to illustrate like all 100,000 paths, but here we have a look at the first 5 paths, and you see it's pretty simple, only a couple of lines of code, and you are done with a nice graphical representation of the simulated paths. But usually it's not that you want to graphically illustrate the simulated paths. You want to use these paths to, for example, value a European call option. In this case, we assume we have a standard European call option with a fixed strike of 105. The Monte Carlo estimator is displayed here, and such a valuation procedure with Python is pretty easy to implement. In Python, this might take on the form as you see here. You have an assumption for the strike. You sum over the inner values as calculated from the simulated path at the end of the period, and you just have the mathematical expression representing the Monte Carlo estimator, and you can print it out here. I just round, or usually round the things to 3 digits to not have kind of too many digits, which is kind of unnecessary when we think of currency units in that case. But you could also use a list comprehension, which might be considered a little bit more Pythonic. In the end, it has the same effect, so to say. You end up with the same result, but this very syntax much more resembles the mathematical representation. You have your Monte Carlo estimator here in a single line of code, and you can say, well, I've translated my mathematical equation into a single line of Python code, and this is, from my point of view, what makes much of the beauty of Python syntax, that this is not kind of an exception. It is more kind of a general rule that whenever you have kind of a financial algorithm, typically you are able to translate a single line from the mathematical representation of the algorithm into a single line of Python code, which in the end makes for a very compact and typically rather good readable code. But let's go on to the NumPy world. What brings NumPy to the table? Well, NumPy brings very, very powerful vectorization capabilities. So here we see a lock version of the discretization scheme, which allows us to use NumPy's vectorization capability to the fullest, which means in the end, we have a function here to generate 100,000 paths in the end, which consists mainly of a single line of code. So there's no looping anymore, if we call it, from the other function in pure Python. We had a nested loop with the outer loop going over all the simulated path, and the inner loop going over every time step to collect or to simulate a single path, step by step. Here in this case, you see we have a fully vectorized version, but with actually the same result. We have quite a compact syntax. We can say the algorithm is fully NumPy. But there is also the other advantage, already mentioned before. It's we observe a considerable speed up here in this case. If you recall it, we had almost 27 seconds for the pure Python version. And here in this case, you see that we only need 1.25 seconds. So a significant speed up that we observe. And in this sense, we have made use of both the compact syntax of Python, NumPy's vectorization capabilities actually, and we also gain in terms of speed, and that we are like, let's say 20 times faster. Very, very nice, just by using kind of a little bit different approach to the whole problem. To calculate the Monte Carlo estimator for the option value is actually pretty close with NumPy to the list comprehension syntax. You see here we have again full vectorization. Full vectorization in the sense that we have only a single line of code where all the operations over the last, which means that have simulated index level values at maturity are taken as given as a vector actually, and we do vectorized operation on these values and end up with quite compact and again pretty close Python line of code when it comes to the comparison with the mathematical description. So at least NumPy in that sense can keep up with the list comprehension syntax that we've seen before from Python. So we are not losing anything here in this place. Let us come to the other numerical method that I want to present. It's binomial option pricing with NumPy. This typically is not that computationally demanding, but depending on the number of time steps that you choose, it still can become quite a demanding algorithm to implement and to execute in the end. Here, just for the sake of completeness, I'm presenting all the assumptions, the numerical assumptions, but this is just for records when you later follow the slides or want to replicate what I'm presenting here. And let's have a look how it looks like if we use, again, only pure Python, so to say, for binomial option pricing. But pure Python in this case, I want to present is not completely correct because the loop heavy, I will do it a little bit smaller that you see the whole thing. It's not about the details here. It's just that you get a grasp of the structure of this function. Actually, again, it's not pure Python. I use indeed NumPy arrays, but I implement Python loops on the NumPy arrays. This for a special reason, which will become a little bit clearer later on. But for the time being, if I would work with lists or whatever, this would look the same. But the point I want to highlight here is that we have a couple of loops. We have actually 3 nested loops in this single function. With the first nested loop, we calculate the index level, so to say the simulation of the path. With the second loop, we calculate the inner values of the option. And with the third loop, at the very bottom of this function, we do the valuation via backwards induction. This could be implemented differently. There are much more efficient ways to do it, but this is just to illustrate how it could look afterwards with Python and what speedups we can achieve with Python performance libraries, which will be applied to this function later on. But again, we have 3 nested loops when we implement it in like kind of a loop-heavy implementation approach here. Let's execute the function and calculate the value. This takes quite a bit of time. It's not that long. It's not as long as simulation before with pure Python, but still it takes 3 seconds for this particular simulation. I think we are having here like 1,000 time steps for the binomial option pricing model. 3 seconds, again, in this case, is our benchmark value. Let's go on to NumPy. How does binomial option pricing, the very same algorithm, look with NumPy? Here in this case, you see, maybe a little bit more compact algorithm. What is left is only a single, so to say, non-nested loop, a simple loop. Again, remember we had 3 nested loops beforehand with the loop-heavy implementation approach. Here in this case, there is a lot of, when I go with the mouse over it, a lot of NumPy vectorized operations that are going on. They might not be clear at first looking at it, but if you step through them, and this is one of the examples that I have in the current book, Python for Finance as well, where we step through every single thing that happens here to illustrate what's going on behind the NumPy scene, so to say. But at the lower end of this algorithm, you see there is one single backwards iteration loop left for the valuation procedure. But again, it's much more compact than what we have seen before with the loop-heavy implementation. But it's not much more compact. Again, we also see a huge speed up. Remember, we had 3 seconds before, and now we end up with, when we use the timeit function and have a couple of loops, we end up with less than a third of a second, in this case exactly 265 milliseconds. So a speed up of more than 10 times by just moving from the loop-heavy Python implementation to the more compact vectorized NumPy approach. But it can be done better. But before we come to the even better, which means faster version, let's introduce a couple of performance libraries. The first area, so to say, which I want to touch upon is dynamic compiling. Number is kind of a rather recent project by Continuum Analytics. It's an open source NumPy-aware optimizing compiler for Python, and it uses the LLVM compiler infrastructure to compile Python bytecode to machine code, especially for the use in the NumPy runtime. So this makes it attractive, and this might explain at this stage why I have chosen the NumPy arrays as the basic data structure for my loop-heavy implementation, which I presented first when it came to the binomial option pricing model. But to show what number in principle can do for you, let us have a look at an introductory example. The introductory example, it's not a financial one, it's just to illustrate where number can really help. And it can really help with things or algorithms that have such a structure, which are loop heavy, where you see a nested loop like this. And this very function, this doesn't do anything but to count the number of loops actually. So it's just to illustrate a point. Here in this case, you see there is an outer loop, which goes from 0 to n-1, and we have an inner loop, which increases the number of loops with the state of the outer loop. So this can be quite a compute-heavy sort of algorithm. And if you think of NumPy implementation and are used to these, and you want to implement such an algorithm where you, in principle, only need the aggregate result, the aggregate running result, and using NumPy arrays, which make the implementation with NumPy really, really memory inefficient. You would need huge arrays, which would be, which would need a huge amount of memory. And this is, of course, something you want to avoid. And there is a solution to that. But before we come to the solution, let's assume n equals 400. And just to provide this parameter to the function and execute it, we see we have 31 or almost 32 million loops with this assumption of n equals 400, and the execution takes 9.7 seconds. Now let us use number, which I introduced previously. With number, the only thing I have to do is to import the library and to call the function JIT, which stands, of course, for just-in-time compiling, to my Python function, which I don't have to change. I don't need any decorators. I don't need any static type declarations or whatever. I just apply the JIT function to my pure Python function f. And I end up with a Python callable compiled function. In this case, I just invoke it one time to complete the compiling. There's a little bit of overhead involved when you execute the compiled function for the first time, but you see this is the compiled function delivers the same result, the 32 million loops, which are simply counted. But now let's have a look at the timing of this. And you see here the speed up is really considerable. Coming from more than 9 seconds, now we only have 34 milliseconds for the whole execution. This is actually kind of the, I wouldn't say the best you can get, but many benchmarks, for example, comparing number in these particular cases to Python show that the results are similar. I have also an example in my current book where I compare the performance of Python and number for certain algorithms with this structure. And it's kind of a pretty simple approach, but nevertheless, you get almost optimal results. It should be as fast as a pure C implementation or C++ implementation in the end if everything goes well. But this was kind of a sandbox example. Now let's apply the technique, the performance library, to the binomial option pricing, which is a much more interesting algorithm indeed. The application is actually the same. You just have to call the JIT function to the Python function. You remember with the 3 nested loops, this is the function we chose here. And again, we invoke it for the first time to complete the compilation step and to avoid the overhead involved. And you see here right now, when I execute the compiled number function, we end up with a speed of 100 milliseconds. If you recall, we came from 3 seconds for the Python implementation. We get down to 265 milliseconds with the NumPy approach, and here using number to just-in-time or dynamically compile our Python function, we end up with a performance which is roughly 2.5 times faster even than the NumPy version. And it's also for certain algorithms much more memory efficient, especially for algorithms which have kind of the structure as the nested loop presented before. So Python, this is the basic message, doesn't have to be slow, even when it comes to the sequential execution of a function. But Python can even be helpful, and this is the next topic, when you want to implement a parallel execution. And in this case, I choose IPython. I could have chosen also, for example, when thinking of a single machine, the multiprocessing module of Python. But the IPython parallel module is actually as easily applied, I would say, and it's a little bit more flexible when it comes to scale over a certain number of nodes. At least there are clusters in production with IPython parallel with up to 256 or even 500 nodes, but there's kind of a point when it becomes not that stable anymore. So it's not for the largest application in the world, but still it's a pretty efficient way to harness the power of multi-core or even multi-node architectures, which means clusters. What we want to implement is the least squares Monte Carlo algorithm, which is the Monte Carlo algorithm, or the most popular one, to value American options by simulation. It has been published in 2001. And what we will observe is that we gain almost linear speedups in the number of cores, actually, when we apply IPython parallel to such a problem. But the LSM algorithm, as presented here, in this kind of a little bit more complex function, details are not that important. You might even replace this with any other kind of algorithm that is of interest for you. Basic message is having these computationally demanding algorithms like LSM, which is much more computationally demanding due to the involved regression step as compared to the European option valuation, IPython parallel might prove a valuable tool when it comes to parallelization. But before we come to that, let's first set the benchmark again with the sequential calculation. Here you see a function which actually replicates the option valuation exercise as presented in Table 1 of the seminal paper. There you will find 20 different parameterizations, which we will see here. So in that sense, we do 20 option calculations for an American put option for the different parameters as displayed here. Again, details are not that important. The basic message is 20 times American option valuation for an American put option by the LSM algorithm. Here you see the results. This is actually maybe not that as nice, but with the same content, the Table 1 replicated with the results for the single options, and you see the sequential calculation takes 23 seconds, almost 24 seconds to implement on my local machine, on my computer. So there's not kind of a high performance thing. This is just a regular notebook where this has been implemented on. There's nothing special about the hardware in the end. But what we will see, I have 4 cores in my notebook, and we will see hopefully an almost linear speed up when we do parallelization. Let's have a look at what it means to do the parallelization. There's not too much involved to apply these advanced techniques, actually. What we have to do is to start a local cluster at least, where we work only locally or on a single server node, actually. I can do this via the shell command IP cluster start, for example, 4 threads. When I have 4 cores with hyper-threading, I could even use 8 threads, but wouldn't expect to scale it linearly with threads, actually. But nevertheless, no matter what machine you have, even if you have only 2 cores in your machine, you will see speedups. Once we have started this up, and by the way, you can also start this up via the dashboard of IPython Notebook if you work directly with IPython Notebook. It's a much easier way because you can start the local cluster with the profile tab or the cluster tab of the dashboard of IPython Notebook. In addition to that, there's only a couple of lines of code that we need to add. We have to define the cluster profile for the local installation. This is my default one, which is stored in my profile of IPython Notebook. And I have to define a client and to generate a view given my client. And here it shows the load balance. Here you see this is very, very compact, only a couple of lines of code that I need to add. And the function actually to do the parallel variation looks pretty similar to the function where we do the sequential calculation. The only thing that changes is that we now asynchronously apply our function to the view just defined before. And we have to wait until every single process is finished. These are the two major things. So in a sense, we only changed 2 lines of code, and we already have implemented our parallel distribution, our asynchronously distributed calculation with multiple cores of the very same problem. There's no change to be made to the original Python and NumPy-based algorithm. And here we go with the parallel variation. You see we have started with almost 24 seconds, so there's not really a linear speed up. There's, of course, overhead involved. So it's more or less a 3 times speed up. We see we are below 8 seconds. But this is still considerable, taking into account that we have just added maybe 3 lines of code and changed 2 lines of code. So I'm aware of a couple of approaches where you have much, much more to do in order to get this size or this magnitude of speed up when it comes to analytics tasks. Just to make sure that we have calculated the same values, here you see the results from the parallel execution. This, so much about the basics of derivatives analytics with Python. We've seen 2 important numerical methods, and we've also seen 2 very interesting performance libraries. The first, Number for dynamic compiling, the second one, IPython Parallel for parallel execution. But I now want to show what it means to work with DX Analytics, our derivatives analytics library, to do derivatives analytics with Python in a more, let's say, compact and standardized fashion, where you don't have to take care of the details, where you have kind of a very supportive infrastructure to implement derivatives analytics tasks. First, a brief overview and the philosophy behind it. DX Analytics, as I said, is a Python-based derivatives analytics library, which means in the end you just do import dx or from dx import star, and you have all the functions available. It allows for the modeling, the valuation, and the hatching of complex multi-risk, multi-derivatives portfolios and trades. To accomplish this rather comprehensive goal and approach, we need the general risk-neutral valuation. This is more for the experts now listening. This is not kind of the Black-Scholes single parameter or single risk factor approach where we end up with a closed form solution. This is more the Harris and Krebs-Pliska paradigm of the fundamental theorem of asset pricing, where we have kind of a number n of risk factors and we have contingent claim pricing in a very general fashion. This is actually what is implemented here in DX Analytics. To reach the generality, we only can use Monte Carlo simulation as a numerical method. If we have multi-risk derivatives or even multi-risk derivatives and portfolios composed of these derivatives, there's only Monte Carlo left that you can use to do that. But what we also use is Fourier-based formula for the speedy calibration of the models. So for the calibration to plain vanilla options, we use Fourier-based formulae, which are of course much, much faster than the numerical methods like Monte Carlo simulation. You can have arbitrary option with single and or multi-risk underlyings. You have European and American exercise features. And in the end, it's completely implemented in Python, mainly harnessing the power of the approaches which I've implemented before. And another assumption surrounding our library is that hardware is not a limiting factor. So as of today, with all the clusters and the availability of computing power as a commodity, we didn't think of this as a limiting factor for what we do. Global valuation at its core means that we have a non-redundant modeling approach. So for example, a risk factor, think of the German DAX index, for example, is only modeled once and not twice if it's used twice. So we reach consistency in terms of valuation, but also in terms of the simulation and the risk aggregation. In the end, we always have a full revaluation. There are no short steps or approximations or whatever. We always have a full revaluation of everything per path, actually. And single positions are consistent also in the end with a portfolio view taking into account all the risk factors and the interactions between like correlations and so forth. But let us have a look at a brief multi-risk derivative case study. Now there will come a couple of slides which have lots of lines of code. After we have imported the capabilities, actually it's mainly a selection of classes, of rather powerful classes from DX. We have to first define our risk-neutral discounting environment. Here we take the most simple model available in the library, and you can think of it's a constant short rate. We just assume a constant short rate of 0%. And for example, we can start working with this. We will need this, for example, like the discount factors to discount cash flows occurring based on the derivatives that we will model later on. But this is just to illustrate, and the details are not that important. Again, you can get back to the presentation, which is hosted on my website. We need to define market environments. Market environments are actually classes or instances of classes which model the complete set of data necessary to either do, for example, a simulation of a geometric Brownian motion or jump diffusion, as in this case here, or to value an option. So this is, again, a collection of input data where data can also be a more complex object like the discounting factor, but this is then used by the evaluation classes and the portfolio classes to come up with risk-neutral values for single positions and or the portfolio. So we need to provide a couple of parameters, of course, for the geometric Brownian motion starting value, the volatility, the currency, and we have to define for the portfolio later on which model we are referring to here in this case. For the jump diffusion, there are a couple of more parameters that we have to take into account. In addition, we have the lumber, which is the probability for a jump per year. We have the mu, which is the expected jump size in percent, and we also have the volatility of the jump size, and again, of course, currency. And the model that we choose here in this case is the jump diffusion. For the valuation to follow, we have to add a couple of more variables, like the number of paths. We want to implement the frequency, which here is defined as weekly. We have to add our discount curve and the starting date and the finding date, and we can add these or this valuation environment to the other environments of the previously defined environments for the underlying risk factors, but simply calling the method at environment and providing the just defined valuation environment. So our market is pretty simple. So this is not a complex thing in a sense that we only have two risk factors, and we assume that for the time being these two risk factors are correlated, strongly positively correlated with 0.05%. So or not percent, correlated with a value of 0.05. This is more correct, actually. Now, going forward to the risk factors, defining our market. We have a couple of different simulation models available. Again, I repeat it, here we use the geometric Brownian motion and the jump diffusion, so that these are the two model classes that we need to model, so to say, our market. The next step, once we have defined our risk factors, is to model the European maximum call option, which is actually our case study in this case. A European maximum call option, in this case, we have just to define a majority, currency, and add the valuation environment to get everything right here. And of course, we have to provide the payoff. And a maximum call option, here as you see it, just says, or is a call option, but where the relevant value, defining the inner value, is composed again of a maximum term. So we take the maximum of the maturity value of the first risk factor and the second risk factor. So it's a little bit more complex than a single risk factor option, and this is an option which falls into the class of correlation option, which means that the correlation between the risk factors has an immediate and sometimes significant impact on the value of this option, which we wouldn't observe if we just have a single risk factor option. Then, of course, correlation with any other risk factor wouldn't have any impact. Now we can value this maximum call option by simulation. To this end, we need a valuation, an instance of our valuation object, which is called in the library valuation MCS for Monte Carlo simulation, European exercise, and multi. Multi stands, of course, for multi-risk. You have to give it a name and to provide the environment for the maximum call option, to provide the set of the assets, the underlyings, which means the risk factors, and also the correlations between the assets. Correlations here is, of course, a list with a single value only, because we only have two risk factors which are correlated again by 0.75, which can be considered strongly or highly positive. Now, once we have defined this, everything else is pretty close, pretty simple, pretty efficient. We can call on our instance of the valuation class the method present value, and the class, the object, gives us back the risk-neutral present value. Here in this case, 5.1. You should remember this particular value, because we will have a second scenario and we'll compare the value to that. But we have also the capability here to calculate, for example, the delta with respect to the first risk factor, to the geometric Brownian motion, which is something rather special, because we are not working with a closed form analytical formula like from Black-Scholes, for example, where it's pretty simple to have an analytical solution even for the delta. No, we have a complex model here for a complex multi-risk derivative, but using advanced numerical methods, we are able to derive the numerical delta here with respect to the first risk factor. And as another example, we can also derive the vega, the sensitivity of the option, with regard to volatility changes, in this case with regard to the second risk factor. So you see, again, this very important factor for risk management and hedging purposes is pretty easily calculated just by calling the method vega on the object and providing the risk factor with respect to which we want to calculate the vega. But usually a graphic says more than a couple of lines of code, so let's do a graphical analysis with our just defined valuation object. If I go forward, I'm not sure whether the presentation is going forward, because now we are moving forward, because I just rechecked with the what you guys see. Actually, I was one step ahead, but now we should come to the graphical analysis. Here we go. The graphical analysis, the first one, so to say, we want to do with regard to option statistics is with regard to the present value of the option given different initial values for the two underlyings. This is just a simple exercise. We have a nested loop where we loop over different values for the first risk factor and then over different values for the second risk factor, ending up with a grid of values, just collecting all the values for later graphical representation, and moving one step further, and in the hope that it will be transmitted rather quickly, we should end up with a graphical representation of the present values in 3D plane. Here we go. Now you should see it. And you see as a 3D representation now for our multi-risk derivative, the values in 3D given different initial values for the two risk factors defining the the maximum call option. The second is with regard to the delta. When you remember, before I showed you the method call to calculate the present value, then I had this brief example for the delta with respect to the first risk factor, and then the example with respect to the vega of the second risk factor. But now we will do the same thing what we did with the present value and have a graphical representation for the delta in 3D space, which when you have a closer look and maybe a longer look when you later on revisit the presentation, makes completely sense when you're used to these kind of options. But still, it's kind of a non-standard representation which is pretty easily implemented with our library. The next and last example is the surface for the vega with respect to the first risk factor. Essentially, the calculations are the same. We have a nested loop, looping over different starting values and calculating for the different parameterizations the single values. This is what you see right now. Here, the very same approach, and now you see the vega surface, which has, of course, a completely different shape, which is with regard to the numerical values in a completely different dimensions, so to say. Our delta is, of course, below 1. Here you see like vega values up to 12. Mainly, I hope that the colorization helps a little bit with reading this 3D. So you see, with DX Analytics, you can do lots of analytical things that you usually cannot do when you rely on like closed formulas, which are not that flexible when it comes to multi-risk derivatives, or are even, or there aren't closed form solutions available even to do these things. But with the library, there's rather Pythonic approaches to implement typical things that you might be used to in derivatives analytics with kind of more simple models and more simple formula, which translate at least from the syntax, not from the numerical methods underlying the whole thing, pretty well to the Python world. And I like to say that our library tries at least to be really Pythonic when it comes to all these approaches. But let us now come to global valuation and to show the impact, what it means to have global valuation and what a change in the correlation means. Remember, we have been in kind of a rather highly positive correlation scenario when it comes to the two underlying risk factors. So what we want to do now is we want to have a look at two selected paths only. And the two paths in the standard, in the benchmark case, are highly positively correlated, and the next graphic that you will see illustrates this. There's a highly positive correlation. The two paths for our two risk factors move almost in tandem. For the jump diffusion, we observe no jump here, so I have chosen these just to illustrate that they indeed move in tandem, actually. Now what we want to change is the single main assumption of positive correlation to a negative correlation scenario. It's actually the only change that we want to make. We change from, and hopefully the screen goes on, we change from plus 0.75 to minus 0.75. And when we do the valuation again with the new parameters, and here actually with a new valuation object that we have to redefine because we have to provide the new correlation structure, you see that with the negative correlation, the value of our maximum call increases drastically. It increases from 5.1 roughly to 6.6 roughly. So we have a significant increase. And this is, again, what is usually meant by correlation options, that these options are significantly influenced, or their value is significantly influenced by the assumptions and or the real world correlation between the risk factors defining the option. And last but not least, we can have a look at the very same two paths that we have been looking for at beforehand, because before we have seen they really move in tandem. They're pretty close to each other over the whole period that we are considering, which is actually the year 2014. But when you see the next picture, you will notice that, of course, we see something completely different. Here, this is what is really meant by global variation. We have consistency over single paths. In the new scenario, with the same random numbers, we see now that they move in almost a complete opposite way. And this is what we mean by global variation, which leads to consistencies in valuation both as well as in risk management and risk aggregation over a single pass. To illustrate something that we have been seeing before, I've also brought with me an example for the parallel valuation of larger derivatives portfolios, because so far this was kind of a very simplistic example with two risk factors only. The next example will not enlarge the space by the number of risk factors, but at least by the number of options. So we had only one option with two risk factors. Now we restrain ourselves to a single risk factors, but we will have an example with 100 options. So here the market environment again. Of course, we need, even for large portfolios having only a single risk factor, we need the market environment. We also, as you will see on the next slide, we need a market environment for the American put option, of course, and the valuation environment. And in the end, we define, instead of a single position only, you see here is the lower loop actually, and in this loop at the very bottom in the input cell 5, you see that we define 100 positions which we will then put into our portfolio, which is the next step. Actually, we haven't seen the portfolio functionality yet, but with the just defined portfolio positions, we can take these and put all these positions, be it 100, be it 500 or whatever. This only depends on the hardware and on the infrastructure you have available, how complex your portfolios can get. Python and our library will take care. In this case, we have 100. And you see the definition of the portfolio here for the sequential calculation. And the sequential calculation, again, as our benchmark case, takes 9.33 seconds in this particular case, actually. So 9 seconds as the benchmark. And you see one parameter input value that we have set in the definition of the derivatives portfolio is parallel equals false. The next definition is exactly the same. The only thing that we will change with regard to the definition is the parallel flag. This will be changed to true. And of course then VX Analytics will, again here on the local machine, on my local machine, will apply parallel both simulation and valuation. So the speed up that we observe should be, and here you see it right now, almost again linear in the number of cores. So with 4 cores we see a speed up of a little bit more than 3 times. The wall time here in this case is 3 seconds only, and this is significant if you consider once again, here indeed you can't even speak of effort. This is just to provide the flag parallel is true. And if you think of more modern architectures like 32 cores in a single node, then you would see here a speed up of roughly 30 times actually. The last topic I want to come to is the benefit of web technologies for derivatives analytics. Web technologies is something, when we started out in derivatives analytics with Python, it was something we almost from the beginning were following. So we started, of course, with a prototype like stuff on a desktop with GUIs and so forth. But even 10 years ago, it was almost clear that web technologies will be the thing of the future. So what I brought with me here in this part of the presentation is a very simple example illustrating the benefits of web technologies. Actually, time to market, maintainability, deployment, and scalability are those which I want to highlight, actually. Because not even providing something to the outside world, even providing something within an organization, web technologies can improve on deployment and maintainability. Our example is based on the variation of volatility options. It's, so to say, a somehow older model. Details, again, are not that important. One message, it's based on the square root diffusion, and it's from Greenbichler Longstaff and was published in 1996. And it's kind of a simple, very standard model to value volatility options, actually. The formula that we want to use is a closed formula. Here you see it right now on the screen. It looks a little bit arcane, but it is pretty straightforward to implement it. This one specialty is that the non-central sheet square distribution is needed here. So this is not even special. It's mainly something that in Python, and this you will see on the next slide when you see the Python implementation, is let's say pretty straightforward. Again, you see almost every line that we have seen in the algorithmic representation translates into a single line of Python code, actually. And this is the basic function which we want to wrap into a web service. It doesn't do anything but to give us back the value for a certain kind of an option given the parameters that we provide. And we want to provide the parameters via a web service-based approach. And this is what the next function shows. Here we have a wrapper function where we define a couple of parameters. Actually, again, details are not that important. It's more the major message that you should take away with you. We just define the parameters with real names. We check if all the parameters are provided. If all the parameters are provided, we transform them to numbers because they are provided as a string. And once we have everything checked and everything is clear, we call our valuation function to get back the result. So only a couple of lines of Python code. The majority of the code that you see in this wrapper function is mainly about checking whether everything has been provided in the expected way. To now come to a web service, this is even, more compact, so to say. Here you see the function which is called application, which wraps the two other functions, in a sense, to a WSGI application, which, for example, with the Python tool Werkzeug, which is actually the German word for tool. I love German words because I'm German. The Werkzeug allows you to wrap this pretty easily into a WSGI application. Actually, this is something we use quite regularly when we have smaller applications that we want to deploy. And you see there are only a couple of lines of code that we need, like the request that we get. We have to get the option values from the request arguments and the response and so forth. But again, it's not about the details here, it's just a message. There is not too much involved, not heavy coding or sophisticated approaches to come up with a web service for already existing functionality. I couldn't even think of like providing the almost whole functionality of DX Analytics as a web service, but at the moment there's no point in that because you have our other application which is called Decisioner, which is completely web-based. But still, you can wrap so many things pretty easily in a web service. And in the end, once you have such a script which wraps the WSGI application, then you just, here in this case, it's the local example on my machine again. I just call Python and then the respective script, and then it is run here on port 4000 on my local host. And you see, this is pretty simple to start up. On a server, it would look pretty similar. And what we can do now, we can simulate kind of the web service as a local service, and we can use URL-lib, the basic URL Python library, where we need the URL open function from, to simulate our web service locally, actually. This is what you see right now, where we just import URL open from the URL-lib library, define our URL, where the web service is running on, and in the next step, we can just call on this URL and see what it gets back. Of course, when we don't provide anything, when we just call the URL, then it complains that all the parameters are missing. Well, that's true because we haven't provided any parameter. So our wrapper function says we need the v0, the r, the kappa, and so forth. Again, this is what is to be expected. Therefore, we define now a new URL where we provide all the parameters apart from the strike. The strike is the one thing that we want to parameterize, actually. This is the URL para string that you see now defined, and this we can use to actually apply the web service, to use the web service for valuation purposes, not using any kind of like parameterization capabilities or whatsoever. It's just a web service that is running on our local host, and using this new parameter, you see implementing a loop over the strikes, we easily collect the values for 250 different option strikes between 20 and 30 in this case, thinking of volatility. And here this is a pretty quick operation. For the 250 calculation, we only need half a second. which for the given formula and the chi-square distribution involved can be considered pretty fast. And if you now think of a web service running on a powerful web cluster with a huge number of nodes and even cores per node, then you can expect huge speed-ups. And again, the wrapping in a web service is not that complex or a sophisticated operation in a sense. The next slide is just to illustrate the option values. This is nothing special about the web service. It's just to illustrate what we have been collecting. We're almost close to the end. After the graphic, the last topic I want to touch upon is our recent project, the Python Quant platform. Based on our experience, which now spans, as I mentioned before, almost 10 years with derivatives analytics and also interactive financial analytics, and providing decision as a web-based platform already since more than 5 years, we have now started building what we call the Python Quant platform, because more and more we see that people need, let's say, a single place where they can work with Python stuff, where they can do their interactive analytics, even complex analytical tasks, even if they are only, so to say, interactive. They can be computationally demanding and complex under the hood. And this is kind of a good approach, again, when you have a web-based implementation of all the things that you do. And IPython Notebook, I mean, in itself has a web-based approach to it, mainly implemented in JavaScript and so forth. So you can easily deploy it on a server, on a large cluster even of multiple nodes or many nodes, actually. And what we do with the Python Quant platform is kind of wrap IPython Notebook and provide all the functionalities that you have seen before with all the performance libraries, multi-core architecture, easy scalability, also providing DX analytics. We have file upload and download functionalities. We have what we call the PyQuant chat room. And also, of course, Decision is integrated into that. It's kind of a single place where people consider themselves Python quants, and now you see the picture as it looks at the moment, where people who consider themselves Python quant will find anything that they need in their daily work, and where they have capabilities to scale in the background, to share files. I mean, underneath we have a user administration. You can define groups. You have certain read and write rights that you can define. So you can collaborate. You can have the compliance officers having to take care of certain things. You have the quants who build the models. You have the trader who apply them. You can have semi-automated analytics processes, and it can do all the nice things that IPython Notebook allows. And in this case, on a server-based, web-based fashion, and we provide this particular solution both as a cloud-based solution where you have the software as a service, but also as an on-premise solution where you say, well, we have already a cluster, but we don't give our data away. We want to work in-house. There's no problem. This is easily implemented on on-premises infrastructures as it is implemented in the cloud that we use. The last point I want to have, this is kind of my closing plaidoyer, so to say, is why Python for derivatives analytics at all? So if I wasn't able to transport all the good messages that I had for today, this is kind of a summary why, if you are not already using Python for derivatives analytics, and I mean the focus lies on analytics in this case, not about trade description or the management of trades and the modeling of trades. It's really about the analytics. Python has a couple of benefits, characteristics that are, from my point of view, really, really beneficial when it comes to derivatives analytics. On the next slide, you will see kind of a couple of points which I consider the most important ones. When I think back, again, 10 years ago, Python was considered really exotic in finance, and this was at best. I mean, people were saying, are you serious to use Python for derivatives analytics? But today, Python has become a major force in finance. And I think there are a number of characteristics to highlight. The first is syntax. We've seen using NumPy or list comprehensions, or even stuff like symbolic Python with SymPy, leads to rather complex and usually easily readable and very well maintainable code infrastructure. Much better maintainable than a couple of contenders in this space. It's multi-purpose. We have a couple of very powerful domain-specific languages like R, very fantastic in the statistics space, but you wouldn't do kind of systems administration or web deployment with R. This was never meant to be the case, but with Python you can do both. You can have the analytics, the statistics, and you have purchased to R, for example, to keep this particular example in mind, and you have web deployment and production and systems administration. So it's kind of more like a multi-purpose platform language and environment. There's so many libraries available as of today. So we have libraries seen today, for example, which improve significantly the performance given a particular task. But there are also many other useful libraries, and I present in my current Python for Finance book with O'Reilly so many useful libraries like PyMC for Bayesian sampling, or the whole SciPy universe with the optimized functions and so forth. There's so many wonderful libraries, and this ecosystem, for example, is something that really differentiates Python when it comes to comparison with Ruby, for example. Ruby is pretty close from my point of view when it comes to the syntax. It's pretty nice, and it's also very good with Ruby on Rails for web deployment, but it doesn't have the scientific stack, the scientific ecosystem that comes along with Python. The efficiency is, of course, something maybe more targeted towards decision makers. Python speeds up typically all IT development tasks in financial institutions and might be able to reduce maintenance costs significantly. Performance, which has been maybe an issue in the past, I think it's not an issue as of today, because Python has evolved from a scripting language, from my point of view, to a meta language with bridges to all high-performance environments that are available. We've seen a number which bridges the gap to LLVM. We have easy harnessing of the power of multi-core CPUs, GPUs, clusters, and so forth. So it's not like that Python in itself is high performance, but with Python you can harness the power of modern high-performance infrastructures pretty easily. And it's also that Python interoperates seamlessly with other languages. Usually it's kind of, I'm using MATLAB, I can't use this. I'm using R, I don't want to have this. I'm using Java, and no. Python is kind of a good neighbor. So it can be integrated with almost any language or platform or technology you can think of. This is a major point when you have, of course, a legacy code in your organization and you want to add Python to the stack, and typically there are no issues with that. Python can live side by side with almost any other technology. Interactivity, having such tools like IPython Notebook, for example, is wonderful when it comes to domain experts to bring them closer to the business and financial data and to have interactive real-time analytics. Again, think of something like a quant platform based on a very compute-heavy cluster infrastructure. You can then have, indeed, even if you're a big data company, real-time interactive analytics implemented. And also collaboration, of course. Once it gets to the point where you want to share data, share results, want to have easy deployment of Python-based applications, collaboration is, of course, a point. And there are tools. It's not the only tool. We are not the ones that invented the idea of a platform for that, but we are targeting especially the quant space here in this case with the Python Quant platform. And when you get to use such kind of infrastructure, then it's also easy to manage rights and roles within the company, to share easily, and to also, of course, share your data and analytics sites pretty easily across the organization. But this is already my last slide, just a couple of more links that you find when you go to the website and follow the presentation. And I think we now have, at least I have time to answer a couple of questions. And so far I have gotten one question, which is with regard to the IPython notebook. I could make available the complete IPython notebook, but there are a couple of special things which are not executable. So for example, to execute the DX Analytics stuff, you of course need a library. We haven't made this public yet. It will be made public with the launch of the platform. So if you like to, you can go to quant-platform.com. This is currently our landing page for the platform, and you can register for a beta trial. It's not open yet, but we will open it pretty soon. So we are right now in the process of migrating the development environment to production servers. If you're interested and also are interested in DX Analytics and all the other things that I've presented, and especially in the platform, just visit this website. So I just changed the presentation, and you should now see. It's just a landing page, but you can register on this landing page, quant-platform.com again. And when you're in the database, we will inform you when we open the beta trial. and you will be informed as one of the first at all, and will have access to our version of the Quant platform. Yeah, this brings me to the end, but I'm still there, and if you have further questions, I think the platform allows for more Q&A. Now I should click. Now we have there are already many questions. I might want to go through these step by step. Just give me a second because I have to change my screen. Give me a second. I hope it is okay that I don't write. I just pick the question and can answer them via audio. There's one question: are these methods used in production? That's evaluation of option pricing in real time. Yes, they are. Of course, we have our platform already where we use this, but recently with DX Analytics, we make heavy use of the most recent technologies. And this is not made public, as I said before, but it's already in production, in the process, or part of it, in the process of getting into production for our clients where we use it actually at the moment. So it's more kind of an internal thing. It's not provided to the outside world. There's a question about the Python load balancing job distribution hit scaling limits. So the scaling limits of the IPython parallel approach, I was told, I never tried it by myself, but I've been speaking to a couple of people who have used this in production, and some said, well, around 256 nodes, it gets a little bit shaky. Some say, well, we have running clusters of IPython parallel with 512 nodes. So I'm not sure about that, but even the IPython core development team is not that eager to promote these capabilities. I think there are many research examples where it's used with huge benefits, but I'm not aware, for example, of a larger financial institution using the IPython parallel approach on a larger scale. I think this is also relating to the second question from John. How does the Python algorithm scale? How far do they scale? Up to 1,000 nodes, 10,000? Yeah, that's what I was saying. I've never heard of any IPython parallel approach which scaled up to 1,000 nodes, and of course then not up to 10,000 nodes. So usually then you would change actually the library or the basic infrastructure, which means the software, the Python infrastructure, to MPI or whatever you want to use here in this case. There's another question: why are the valuations slightly different under the parallel processing? Actually, parallel processing, both with what I present in IPython parallel and with, for example, the multiprocessing capabilities of DX Analytics, it's always a question of numerical errors. Actually, for example, calculating the same option in parallel with the multiprocessing module, we will end up with, for example, 10 times the same option value when you do the procedure with 10 option values, because the seed value for every single numerical simulation will be the same one. So to say, you're starting always anew. When you do sequential calculation, of course, the Python interpreter generates different variation once it comes to the second option processing. So this is mainly due to the sampling of the random numbers. There's a question about DSL. I actually don't know where I use DSL, to be honest. I might come back to this later on. Which is more powerful, the subject is both Python and related libraries, R related libraries, or Microsoft Excel. As I said, Python is a good neighbor. Python understands itself pretty well with both R and MS Excel. So we are currently, or I'm currently working, for example, with Felix Zumstein, who is the author of the XL Wings library, which has the only purpose to make a seamless integration of Python in Excel spreadsheets. So this is not an either-or question. This is more kind of a question: what are good combinations? If you think of MS Excel, of one of the most widely distributed, easy-to-use, general graphical user interface, then Python is a very powerful addition and language and platform, as we have seen, to enhance the capabilities of Microsoft Excel. And again, if you don't find a well-suited statistical library, there are a couple of Python bridges available where you can harness the power of R. So again, from my point of view, it's not either or the one is better than others. Python works pretty well with others as well, and if you want to use Excel, you should consider, for example, using XLWings and to integrate Python into your Excel world. What is the GitHub URL for DX Analytics? This is a good question. Again, we haven't published it. We haven't decided whether to open source it or not. Sorry, guys. At this time, this might be something for the future. But I can tell you one thing: at least 50% of the library and the basic architecture and the basic classes are presented in the Python for Finance book. So the last 100 pages of the new book, which are not yet out in the early release, but it can't take too long anymore, I've written it up already. It's, again, about 100 pages. It explains the whole architecture, the whole idea behind DX Analytics, and exposes the fundamental classes used from the very simple ones like constant short rates up to a couple of simulation models to single risk European and American valuation classes to the end, also to the portfolio valuation class. So indeed, if you want to have a look at it, it will probably be the best way to buy the book. Then you find 100 pages about DX Analytics. Not all the functionality, but again, we haven't decided how to go forward with that. What about Python in today's finance tools application? For people who are not yet convinced that Python is something good in the finance space and cannot be applied on large scales, please Google up Bank of America Lynch and Python. They've implemented the largest part of their Quartz risk management and trading platform in Python. They have, as far as I know, more than 10 million lines of code of Python in production in their risk management system. The same holds true more or less for JP Morgan with Athena. Google up JP Morgan, Python, and Athena, and you will see that these two, one is the largest bank in the world with 350,000 people, the other one is one of the largest in the world. They both use Python for very core things when it comes to finance, risk management, pricing, and so forth. There's a question about a C implementation. Again, if you apply the right approaches and using things like number, in certain cases you can get to the speed of C. Not in any case. But again, consider the efficiency gains gained by Python. I mean, a typical C implementation for a more complex algorithmic thing could be like, let's say, 500 lines of code in Python. You might end up with 50 or even 25 lines of code only. So it's not only about the speed, but again, using NumPy and other performance libraries, or the NumPy approach even to start with, can get you to speeds that are comparable to the C speed or C++. Again, I asked the last question, which is listed here for me: will the IPython notebook be made available? I could do it, but again, it's not too much of a point in it because the DX Analytics parts in particular are not executable without having the library. It's kind of a no-brainer. So this indeed is what I had. But there are now, there are other questions now coming in. Just let me check what I've answered before. There's a question about the pricing model, business model around Quant Platform. In the past, we have provided decision as software as a service. So typically, you pay for like a year's fee. If you go to the website derivatives-analytics.com, you will find the pricing model for decision, and I'm sure at the moment that it will look similar, at least for the software as a service, for the cloud-based solution, as it looks for a decision platform, actually. There's another question about how you would price all 500 listed US options in real time. This is not what our solution or the whole thing is targeted towards. There are other approaches when you have the listed options, which are pretty standard options. There are approaches available, and there are companies that are pretty good at applying GPUs to do that. This is not what we want to do. What we are more oriented towards is kind of the more complex things. What you've seen, kind of these maximum call options, or even think of hybrid options and so forth, These are typically over-the-counter options, which are not quoted in real time, so you typically don't need to price revalue them in real time or risk manage them in like on a sub-second basis. What we are working with usually are like kind of quantitatively oriented quant funds, which are designing complex structures, for example, vol funds, which are designing complex trading structures involving a couple of options and building complex payoff structures. And this is where our tool is more or less targeted towards. We don't want to replace any kind of a highly optimized library which is able to price thousands of vanilla listed options in real time. This is not the target market. We are more on the financial engineering side. And this is kind of a very different problem to have a complex model where you want to come up with risk-neutral, market-consistent prices. What library model do you use to pull real-time option prices? Well, at the moment, we see us mainly as kind of a tool provider. So to pick the Excel example, Excel in itself does not allow you to pull any kind of option prices. But for example, you get all the nice plugins and interfaces to Bloomberg, to Thomson Reuters, and so forth, where you can pull data into Excel. And this is also our approach. For example, DX Analytics and the market environment approach, you are pretty flexible in kind of writing compact and efficient APIs around whatever library you want to have. So we are currently in discussion with at least one of the largest data providers to write a Python API so that maybe in autumn this year for the Quant platform and for all our solutions we'll have kind of a standardized solution to pull in data, and not only for options but also fundamental data if you think of more like fundamentally oriented financial analysts, and also for stock price data, for historical data, when you think of backtesting and quant strategies. It's mainly the whole thing. And the last question that I have now on the screen is about what is stopping open sourcing DX. Well, this is kind of a more complex discussion that we have internally. It's mainly due to the state of the project, and we would see how far we go. But I think the future will be that we will kind of open source it. But not yet sure about that. Sorry that I can't answer this more specifically. There are a couple of more questions coming in. I'm happy about all the questions that we have right now. Let me see. There's also a question about the precisions and slightly different results when using NumPy, number, and parallel methods. Again, this is, of course, you have certain errors. You have the sampling error, which is mainly due to the random numbers that you use. You have discretization error. I have used, at least in two places, different discretizations for the same SDE. And the parallel methods, again, this is kind of a seed issue. Even when you're using the same library, the seed, of course, influences the random numbers that are turned back. I don't have implemented in the process that you have seen kind of variance reduction techniques. It wasn't about the precision of the variation. It was more about the performance and how the code looks like. But usually, for example, in DX Analytics or Decision, we have built in rather efficient variance reduction techniques where the sampling error shouldn't be that high. So I don't know if you have more questions. Okay. Here are a couple of new questions. What companies provide GPU pricing of listed options? Sorry, I have to look it up. There's one company, I don't know if they are leading, but they not only provide the pricing, but also Creeks and so forth. In real time, they are since years a heavy user of GPUs. If you drop me an email, I can look it up. I have contacts at this company, but sorry that I don't remember the company at this very second. You'll find my email also on my private website and so forth. It should be easy to contact me. Then I can get you the information about that. When will I do my next presentation? Oh, I'm a regular presenter. I recently, when discussing this with someone at the conference in London, I was quite amazed. Over the last 12 months, I attended like 13 different conference events. I've given like 18 or 20 talks. My next conference where we'll speak, we will do a recording of a Python for Finance class, which is in 8 modules in July. If you are in London based and are interested, you can attend this. This will be live recorded. This is 16th and 17th of July. I will then be presenting at the EuroPython in July, I think the last week of July, and also at the PyData, which is at the end of July in Berlin. Both EuroPython and PyData are in Berlin. There I will present. Usually both conferences record all the things, so it will be made available on the web. And then the next thing I think is EuroSciPy in Cambridge, where I will present. So a couple of things ahead. Usually have 1 or 2 events per month where I do a presentation. Again, the question about pulling real-time option prices, this is nothing we have. We are working on. Where does the simple load balancing? This I answered already. DSL is the only thing I don't know where I have used this. Just skipping through the things, I think that I almost answered all the questions. I don't know if there are any left. We are done with the official time, almost. I think we have 4 minutes left. I have even 14 minutes left. But if there are no questions, I at least take this opportunity then to thank you all for all the patience, all the nice questions. Again, it's pretty easy to find contact information for myself. Just visit hilpisch.com, my last name.com. You find also valuable information about DX Analytics and anything else. And once again, for me, it was a great pleasure presenting this webcast to you all guys from around the world. I know there are many people from around the world, and hope to hear from you soon, and look forward to hear more from us when it comes to derivatives, analytics, and Python with finance. Thanks to you all.
Thank you so much, Yves, for presenting an incredible webcast for us today and for sharing all your knowledge and expertise.
Great.
People that attended our webcast today, we thank you for attending and staying with us and asking so many questions, because having your questions really adds so much to our events, and we thank you for that. And we'd like to let you know as we close out the program, we did push out a code to you all in your group chat. So if you didn't open that group chat, please open it before you leave. There's a code in there to save you a little bit of money on Yves' book, Python for Finance. Excellent, excellent book. You can get the ebook today for 50% off and pre-order the print version. If you like what Yves was talking to you about today and showing you, the book is going to have so much more in there that can really help you with your day-to-day. So do take advantage of that discount and get the book. Folks, again, we thank you for attending. Thank you, Yves. This will conclude today's webcast. Goodbye, everybody.